right, hi, welcome. This is Math 145, section 5.1, and let's get started. This is going to be kind of fun. This is probability. So we're just introducing the idea of probability. Probability answers the questions like, how likely is a sum of 7 when you roll a pair of dice? How likely is it that you get struck by lightning? Probability will answer those questions and more. Consider rolling 2 dice. How likely is it that you get 2 even numbers? Or, as I say, a sum of 7. Think about a couple who's about to have children. How likely is it that they have exactly 2 boys followed by a girl, or exactly 3 boys? So we're going to answer questions like this, and we're going to start off by actually using an applet they have on MyMathLab called Simulating the Probability of a Head with a Fair Coin. And what it essentially does is it flips a coin for us over and over and over again. So first off, let's answer part A. What does it mean to have a fair coin? Go ahead, pause me down, see what you think about that, write your answer down, and then come back. All right, so there's my answer. It's equally likely to flip tails as heads on my fair coin, right? So let's get to the applet. It tells me have the applet simulate 1 toss to start you off. Use the graph here to record whether it was heads or tails. And then have the applet simulate 5 more tosses. And then at the end of 6 tosses, what's your proportion of heads? And I'm going to do that part in the applet, and then I'll come back and write everything down the notes once. All right, so here is the applet from MyMathLab. So here it went, it flipped a coin and it was tails, right? And it flipped another and it was tails, and another, it was tails. In fact, I did this for 6 tosses and only the very last one did it get a heads. So you'll notice 1 out of 6, or about 17% heads. I did it again here. So first one tails, second one heads. So you'll notice, and I'm going to pause down here. What it's doing is it's every single time it's flipped a coin, it is recalculating the proportion of heads, and of course showing you the coins, which is kind of fun. And but it's plotting the proportion of heads along this graph. So let's watch it do it a couple more times. And you can see it ended up with the proportion of heads being 2 out of 6, or 1/3, or 0.333, right? Okay, so I'm going to try to copy that onto my paper, and then we'll come talk about it. All right, so once again, let's just talk through this a little bit. The first coin was a tails, and so we had 0 out of 1 as the proportion of heads. And then the second one was a heads, and so we had 1 out of 2 for the proportion of heads. Third one was a heads, so we had 2 out of 3. That was heads, and then so on. And that led us into part D. At the end of 6 tosses, what was your proportion of heads? What does that mean? How many heads out of 6 tosses did you have? And let's write that down. And I'm going to use notation that we're going to see throughout. P of H, meaning probability or proportion of heads, was 2 out of 6. And again, that gave us that decimal equivalent of 0.33 if we wanted to write that. And I think that's all that they really wanted there. And then, and again, just the idea that, you toss coins up and count how many heads. That's something we do in probability. So part E, it asks, what does the horizontal line on the graph indicate? And you will notice that it is right there at a P of H value, or a proportion of heads, at 1/2. And that is in fact the theoretical probability of a heads, which is to say there are 2 sides of a coin, and heads is one of those sides. They're equally likely, And so the probability of heads is 1/2 or 0.5. Let's do part F. We're going to get back to the applet, and this time we're going to have it toss 1,000 coins. We're asking ourselves, what is happening to this experiment, and more specifically to the proportion of heads, as it goes on and on and on and on and on and on. Let's get back to the applet. All right, so it does this, is lickety splickety. There's your 1,000, and just for fun, I did it a couple more times, and we have that graph. And what do you see in that graph? What is happening as the number of flips gets bigger and bigger and bigger and bigger? That's the question we're trying to answer in part F. What I saw in that graph was a lot of fluctuation in the beginning, but as it went further and further out, it certainly looked like the proportion of heads was getting closer and closer to this midline here at 1/2. Again, lots of fluctuation early on, but as I got more and more and more flips, it certainly looked like the proportion of heads was approaching 1/2. And in fact, that is something called the law of large numbers that we see later on in this set of notes. So let's get to it. So here we've got a whole bunch of definitions. So let's start off with probability definition. It's simply a measure of the likelihood of something happening, some random chance event happening, right? Like the probability of getting a heads when you flip a coin. It's random, right? Or the probability that you get a boy when you have a baby. So we really deal with experiments that yield random short-term results or outcomes, like flipping a coin once, twice, 3 times, right? But they reveal long-term predictability. Like you could say overall, the probability of getting a head on a coin is 1/2. So they make that distinction in the book. The long-term proportion in which a certain outcome is observed is the probability of that outcome. So again, over time, as I flip more and more coins, like we saw on the first page with the applet, as over time, as I flip more and more coins, the probability of getting heads was approaching that 1/2, which we say is the probability of getting a heads on a coin. We will see what I call the very useful formula in a little bit, but we first have some terminology. First of all, we have an experiment, something that I'm going to do repeatedly, or maybe simulate with a computer like I just did, flipping a coin. Each time we do that experiment is called a trial. The sample space is pretty important to us. That's a really kind of an important definition there. It's going to be denoted as capital S, and it will be the collection of all possible outcomes. We're going to use curly set brackets to talk about that. So like for flipping a coin, S, the sample space, would be the set of getting heads and getting tails, right? Separated by a comma. We'll see that in a lot of applications. Next definition, an event is some collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. Examples are possibly rolling a 6 on a die or getting 2 heads when you toss 2 coins. We will denote events with one outcome, sometimes called simple events. I don't particularly personally use that notation, simple events, E sub I, but you can see it from time to time in the book. In general, events are denoted using capital letters such as E. You'll see me do that a lot. The probability of an event E is denoted by P of E. And we did talk about that a little bit earlier because I used that notation earlier. Definition, very important. A success is considered to be the event we are interested in. If I'm talking about the probability of getting a heads, like on the last example, a success was heads on the coin. And every time a heads came up, when I flipped my coins, that was a success. All right, let's do number 2. It says, consider the probability experiment of having 2 children and recording their sexes. I know it seems weird to think about that as an experiment, but there it is. Identify the outcomes of the probability experiment and write them in set notation, labeled as S. So let's go S equals curly set bracket. Okay, I'm having 2 children. I'm thinking about their sexes. Well, I could have 2 boys, right? So I'm going to write that as boy, boy, comma. Another thing that could happen is I could have 2 girls, right? Girl, girl. Well, of course, I could have a boy and then a girl. I could also have a girl and then a boy. Whoops. So those are my 4 possibilities for having 2 children. Just talking about that notation there, that E sub 1 could be considered, that E sub 2 could be considered, what I decided as my second choice, and so on. And simply the order in which I decided to write those down determined what subscripts E sub 1, E sub 2, or whatever. So don't worry about the subscripts themselves. It just means the first possibility, the second possibility, etc. Okay, letter B. Define the event E having exactly 1 boy. In other words, which outcomes comprise this event? Use set notation. So I'm going to write E, curly set bracket, equals exactly 1 boy. Well, boy, boy doesn't have exactly 1 boy. Girl, girl obviously doesn't have exactly 1 boy. Boy, girl is one of these 4 outcomes in 2A that has exactly 1 boy, and also girl, boy. Okay, let's go on to the next page. All right, this is the most important thing you will see, and that is the formula for probability. Keep this guy in your head. We are saying that the probability of some event is the proportion that compares the number of successes to the number of possibilities. This does assume the possibilities are equally likely, like the heads in the coin, the heads and tails on a coin, right? Probability of an event equals the number of successes over the number of possibilities, simply put. Okay, let's do number 3 to show off this wonderful little formula. Return to the experiment of having 2 children. What is the probability of having exactly 1 boy? So I will write it as this, but remember how we defined that as the event E? I could write it as P of E. Now, I want to think about number of successes over number of possibilities, and that is so key. That's all that formula is. That is so key. Think about this. When you have 2 children, there were 4 possibilities, right? There were those 4 possibilities we wrote down on number 2A. How many successes were there? Well, there was a boy, girl, and a girl, boy. 2 successes. So simply, probability of having exactly 1 boy is 2 out of 4. If you wanted to reduce it, you could. But I could take either of those as an answer. I know sometimes they say don't ever leave answers unreduced. But leaving it as 2 over 4 gives you some idea as to how the number came to be. 2 successes, 4 possibilities. So there is some benefit to writing it that way. Let's look at the next thing, which is deducing 3 important rules, and they are called the fundamental rules of probabilities. Let's look at them together. Can the probability of an event be negative? Think about this. The probability of something happening is number of successes over number of possibilities. If this were to be negative, then that would mean one or the other of these were negative, and that just can't happen, right? The number of successes or the number of possibilities can never be negative themselves. So, probability can never be negative. Part B, can the probability of an event be more than 1? Think about that. Probability is number of successes over number of possibilities. So for this to be more than 1, think about it, it's a fraction that's more than 1. That would mean for the fraction to be more than 1 would mean the number of successes would be more than the number of possibilities. But how would you do that? Right? Think about it. Flip a coin, 10 times. Now count the number of successes. Can that ever happen? never can happen, can it? So probability cannot be more than 1. Okay, part C. What's the sum of the probabilities of all possible outcomes? This kind of comes into play a few different times when we're doing more complicated problems. So let's think about this. Complete these tables below to answer this question. Okay, think about tossing a coin. Let's see. How, if your outcome is heads, the probability is 1/2. For the outcome of tails, probability is 1/2. Total is 1. Let's think about this. Family with 2 children. For each of those outcomes, those are the probabilities. 1/4 all of them, wasn't it? The total is 1. The point of this is that the sum of all probabilities of all possibilities is always 1. Okay. There's 3 types of probability they talk about in the book. This is kind of nice to see. The classical method, also called theoretical probability, was used when we thought about the probability of having exactly 1 boy with 2 births, right? The outcomes are all equally likely, and that's really important in this method. And you basically just count up the number of successes and number of possibilities, right? To use that very useful formula and figure out your probabilities from there. The empirical method basically means you're going to experiment to find this probability. It's also called experimental probability for that. So you actually do the experiment, you actually toss a coin 1,000 times or simulate it, or you, strangely enough, right, this wouldn't work very well in real life, or you really have 2 babies 1,000 times and see what happens. That is the empirical method. We actually do the experiment. And the probability formula just changes slightly with number of trials on the bottom there, and not a number of possibilities as before. Then there are subjective probabilities. We're talking about weather forecasting probabilities. Horse betting is another example of that. We don't really talk much about that kind of stuff in this section or in this chapter, but it is clearly a probability that is out there. Okay, look at that definition of impossible and unusual events. Pretty much what you would think. If an event is impossible, it means it can't happen. The probability is 0. Can't happen. Think about that. Probability is 0, meaning it cannot happen. All right. If an event is a certainty, well, then it really will always happen, and the probability of that event would be 1. And an unusual event, right, would mean it doesn't happen much, right? Well, what is much? We're going to define that. So an unusual event will be defined as one that has a low probability of occurring, usually lower than 5%, but not set in stone. So let's look at this really quickly. Number 4. Consider the probability model to the right that shows the probability of selecting each color in an M&M bag. So let's say I opened up a brand new M&M bag and I counted out the brown, the yellow, the red, the blue, etc. M&Ms, and I found that 11% of them were brown, 15% of them were yellow, etc. Okay? Number A, verify that it is a proper probability model. That is, make sure it adheres to the fundamental rules of probability, which we did just talk about on the last page, but they were basically these guys here. Make sure the probabilities are all between 0 and 1, and make sure they add to 1. So we're going to do that. So of course you look at each probability that they quote you and make sure it's between 0 and 1, and it certainly looks like that is true. Now, do they sum to 1? So add up the probabilities that they are giving you, and you're going to see it actually is 1. So they do that as well. So yes, it's a proper probability model. Yay. Okay, what is the most likely color to select from the bag? What do you think? What do you think? I'm going to go with, what are you going to go with? Blue. Because it has the highest probability. Did you guess that too? All right, cool. All right, next one, number 5. What does it mean for the probability of an orange to be 0.23, as it says on the other page? Just label each sentence as true or false. I'm just going to go through these and see what I think and try to talk out loud. Okay, A, if you select 100 M&Ms, you would expect to get around 23 orange ones. That nice word around there is all very important. I want you to look at C. If you select 100 M&Ms, starts off the exact same way, right? You should get exactly 23 orange ones. See how different that is? Just that different word can make all the difference. A says, if I select 100, I'll get about 23. That's really what the probability is more about. Not exactly 23. I'm not guaranteed to get exactly 23 because, every bag is slightly different, right? So I'm going to call A true, but C false. Okay, part B, going back to B, it says getting an orange M&M would be considered an unusual event. Well, an unusual event is the probability is less than 0.05 or 5%, and that's not. So that's false. Part D, getting an orange M&M would be considered a certain event. That would have to be it equaling 1. It would always happen. It would be certain that I would get an orange. Well, that's not true as well. E, getting an orange M&M should happen about 1/4 of the time. About 1/4 of the time. And that's 0.25, right? 1/4 is 0.25, and 0.23 is pretty darn similar to that. Okay, I'm going to go with true on that. F, an orange M&M is more likely than a yellow M&M. G, I don't know, what did it say? What was yellow? Yellow was 0.15. So the probability of yellow was 0.15. Is an orange more likely and then a yellow? Yellow is 0.15. Orange is bigger than that at 0.23. So I would say, yeah, that's more likely. Okay. The optional worksheets here, we are just going to outright cut, so we don't need to worry about those at all. Now, think back to the last part of example 1. That was where we had that applet and we tried to draw out the graph of it as it went out further and for like 1,000 flips of the coin. Recall that the proportion of heads got closer and closer to 50% as the number of trials increased. This is an example of the law of large numbers, and it's simply got something there to say about it. The definition of law of large numbers is that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the true probability. And really, again, what they're just saying, just like we saw, as we flipped more and more coins, the proportion of heads got closer to the true probability of 1/2. Okay, I also have that a little bit differently stated with my orange M&Ms there that you can read. All right, on number 6, we're talking about rolling 2 6-sided fair dice. The sample space is shown below. So if you think about it, you can get a 1 on the first die, right? A 2, a 3, a 4, a 5, or 6, and a 1 on the second die, right? Or you could do a 2 on the second die, or a 3 on the 4, right? So you should be able to see how you can basically get all of these 36 possibilities when you roll 2 dice. And if you've got to think about a probability of some event happening, the easiest way to do it is thinking about how many possibilities are there. If you can think of your sample space, then count the number of possibilities. And then simply put, whatever your event is, count how many of those possibilities are also successes, and you've got your probability. Let's do A. What's the probability of rolling a pair? I'm going to write it like this, meaning the 2 dice display the same number.
Circle the possibilities in the sample space above that would be considered successes. I'm asking you to do that so that you can start visualizing what I mean by number of successes over number of possibilities. So I'm going to go through here and I'm just going to circle the, turns out 6 successes that I had out of those 36 possibilities, and simply put 6 out of 36, or 1/6, is my probability. What about a probability of getting a sum of 7, as part B asks? Star the possibilities in the sample space. I just told you to star them so that they might stand out a little bit better than the other ones. Okay, so I want a sum of 7. I want my 2 dice to add to 7. Oh, here's 1. 1 and 6. Oh, 5 and 2. Here's 1. 4 and 3. Oh, and in fact, the beauty of putting these sample spaces in like that is that the rows and columns, they really add to some nice, some patterns. So I'm going to do number of successes over number of possibilities. And once again, I got 36 possibilities, and I simply count how many successes I have. Coincidentally, the same number as I got before. All right, letter C. What's the probability that both dice turn up as even numbers? I wrote out this sample space so that I could draw on it without messing up the one that I had already drawn all over up above. So let me do this. So dice both even. Okay, so I'm going to look down the first column. It doesn't look like any of those could be successes, but on the second column, I got my 3 successes there. Again, third column, both dice can't be even if one of them is all 3s, so that kind of locks that down. I got those 3 successes. Again, fifth column, none, and sixth column, I've got those. Again, if you can think about a probability question as simply number of successes over number of possibilities, it makes it so easy. It really does. So let's see, I have 9 successes, don't I? Out of that same 36 possibilities, which reduces to 1/4 if you care to reduce it. Now, MyMathLab will always want you to reduce it, by the way. I just say on worksheets and on my own papers, I often leave it on an unreduced form because that 9 over 36 gives me more information about, those successes. Okay. This one, number 7, is here because specifically you have one like it in your homework. It says a class has 4 students, very small class, who want to team up to give an extra credit report. A 2-person team will be chosen at random. Answer the following questions. First of all, A, determine the sample space. In other words, list all possible 2-person teams from these people, A, B, C, D. I'm going to write it as S equals. I'm going to go from there. All right. This is how I would think about this process. I have Amanda, Bailey, Christy, and Doug. And you'll notice they're all names start with A, B, C, and D, so we can abbreviate them. So I'm thinking Amanda goes with Bailey, that's one 2-person team. Amanda goes with Christy, that's another 2-person team. Amanda goes with Doug, another one, right? Now at this point, I have all of the 2-person teams that could possibly have Amanda in them. So I'm going to ignore Amanda. I'm going to think Bailey and Christy, Bailey and Doug. Now I've got all the ones that have Bailey in them because I got Bailey paired with Amanda up here. I got Bailey paired with Christy here, and I got Bailey paired with Doug. That's the only ones it could possibly be, right? So I ignore Bailey now, and I go Christy and Doug. Christy and Doug. Now, I don't have to do DC because this is the same 2-person team as CD, right? For the same reason, BA is the same thing as AB. So I don't need to call BA out. And I'm going to write my sample space with all of those options for 2-person teams separated by commas. There you go. All right. Part B, are all of the 2-person teams equally likely to be chosen? Yes, they are. Okay, it's part C. What's the probability that Amanda is chosen? probability of Amanda chosen? Let's again think about this as a number of successes over number of possibilities. Number of possibilities is 1, 2, 3, 4, 5, 6. Okay, number of successes, the ones where Amanda is chosen, looks to be 3, or 1/2 is the probability that Amanda is chosen. A probability Amanda chosen. Okay, what's the probability that Amanda is not chosen? Amanda not chosen? Well, let's think about this as number of possibilities and number of successes as well, but here, number of possibilities is still 6, but the number of successes this time is when Amanda's not chosen. Well, that would be those 3, wouldn't it? 3 successes. Still gives us a probability of 1/2 for that one. What is the probability that Doug and Christy are both chosen? Well, there's only one of those 6 possibilities where that was the case, wasn't it? CD possibility. So it's got to be 1/6, huh? This number 8 is a pretty cool little guy here, just talking about lightning and probabilities a little bit differently than we talk about the probabilities of, say, finding a heads on a flip of a coin. So read this guy over here a little bit, and then maybe if you could try to answer 8. I'm going to read over a little bit and then try to do 8 myself. I am just always struck by the fact that only 10% of people who are struck are actually killed. I had no idea so many people lived through that. Anyway, number 8 says, how do you think they got the figure for 1 out of 1,083,000 for the odds of being struck by lightning in a given year? Now, they are actually using the word odds, and I would just like to say that it's related to probability, but really quite a little bit different. So we're not going to be particular about what we do here exactly, but probably what they did was they took the 300 injuries and deaths and divided it by the population. Odds of getting struck by lightning, think about that, what they thought, well, we'll take the number of strikes, basically, and the population, and divide it by the population. And if you do that, you'll notice you get strikingly close to that 1 over 1,083,000. Okay. Number 9, again, is here because your homework has one just like it. It says out of the 300 people in a large lecture class, 159 of them have their own car. So, part A, if we select a person at random from the class, what's the probability that they have their own car? Simply say number of successes over number of possibilities. There's 300 possibilities for people in the classroom. 159 of them have their own car. And if you do that on the calculator, you're going to get a decimal answer. And if you give the decimal, if MyMathLab asks for a decimal answer, obviously give that. If not, you might reduce it to another fraction. Okay. Part B, if we survey 1,000 similar people, how many should we expect to have their own car? What we're supposed to do here is just take 1,000 and multiply it by the probability that they have their own car. So 1,000 times 53. Basically, this 0.53 can be thought of as 53%. So if you want to think about what we're really doing is finding 53% of 1,000, that could be a good interpretation. Okay, there you go.